We are about to dive into a scientific story with the highest possible stakes. Seriously, this is a cosmic showdown for our entire understanding of the universe. In one corner, you've got the reigning champion of physics, and in the other, a radical new challenger. The judge for this fight is the James Webb Space Telescope, and it's just delivered the first ever evidence of its kind. For decades, there's been this huge cosmic mystery hanging over our heads. You see, everything we can actually observe, every star, galaxy, and planet, that only makes up about 5% of the universe. The other 95%? Well, we've been told it's made of dark matter and dark energy, these invisible ingredients we've literally never been able to find. But what if we've been looking in the completely wrong place? What if the problem isn't some missing stuff, but a fundamental misunderstanding of gravity itself? So, to really understand this cosmic battle, we first have to get to know the reigning champion, Einstein's theory of general relativity. This is the absolute foundation of modern cosmology. But, as you'll see, it's not without its cracks. For over a century, general relativity has been this towering pillar of physics. It is an absolute beast. It's predicted everything from the way starlight subtly bends around the sun to the incredible ripples in space-time from colliding black holes. Its track record is just astounding. It is, without a doubt, the most successful theory of gravity we have ever had. Okay, so this slide really gets to the heart of the problem. General relativity, for all its success, has two major cracks in its foundation. First, it literally predicts its own failure. At the center of black holes and at the very beginning of the universe, it predicts these things called singularities, points of infinite density. And in physics, infinity is a huge red flag. It basically means your theory is broken. Second, to make the theory work on a cosmic scale, we have to invent dark matter and dark energy, which supposedly make up 95% of everything, even though we have never ever found a single trace of them. So this brings us to the challenger, a theory that proposes a truly radical solution. What if gravity isn't a fundamental force at all, but something else entirely? This new contender is called vacuum field theory, or VFT for short, and it flips our entire understanding of gravity right on its head. VFT suggests that gravity isn't fundamental, but an emergent effect. Okay, think of it like this. The temperature of a room isn't a property of a single air molecule, right? It emerges from the collective motion of all of them together. VFT proposes gravity is just like that. It emerges from the collective properties of the vacuum of space. So in this view, empty space isn't empty at all. It's a physical medium, and gravity is just what happens when that medium gets disturbed. And get this one single idea has two absolutely incredible consequences that just so happen to neatly solve general relativity's biggest problems. First, if the vacuum is a real physical thing, well, you can't compress it infinitely. It's got a maximum density. And just like that, the problem of singularities, gone. Second, VFT suggests that this vacuum medium behaves differently in these super low gravity environments out at the edges of galaxies. And this change in behavior perfectly, and I mean perfectly, explains why galaxies spin faster than they should without needing a single speck of dark matter. A good scientific theory doesn't just solve old problems. It has to do more than clean up old messes. It has to make a new, unique, and totally testable prediction that no other theory can. And VFT, well, it makes one of the boldest predictions in the history of physics. So, for years, astronomers have been really puzzled by this strange coincidence. There's this very specific rate of acceleration, they call it A0, where gravity seems to start acting weird in galaxies. Mysteriously, this number is incredibly close to another really important cosmic value, the expansion rate of the universe, which we call CH0. So, is this just some cosmic fluke?
This slide gets right to the heart of the conflict. The standard model of cosmology, which is our current best theory, says this link is a complete and utter coincidence. No meaning at all. According to this model, A0 should be a constant value, the same everywhere and at all times. But vacuum field theory says, no way, it's not a coincidence at all, it's a fundamental law of nature. VFT predicts that A0 is directly tied to the expansion of the universe, and it must have changed over cosmic history. And here it is, the smoking gun prediction. VFT predicts that a knot changes with something called redshift, which is basically just our way of measuring how far back in time we're looking. So, in the early universe, when the expansion rate, or h of z, was much, much higher, VFT predicts that a knot should have been much larger too. So you have two crystal clear opposing predictions. One theory says a knot is constant, the other says it changes.
The stage is set for a definitive test. Now, the crazy thing is, for decades, this incredible prediction was totally untestable. We just couldn't see far enough back in time to know if A0 was different in the early universe. Until now. The James Webb Space Telescope is our cosmic time machine. Its incredible power lets us see ancient galaxies from over 12 billion years ago, a time when the universe was expanding way faster. So for the very first time, we can actually measure the rotation of these ancient galaxies, calculate a knot way back then, and see if it has changed, just like VFT predicts. All right, the stage is set. The theories have made their predictions. The telescope has gathered the data. So what does the first evidence actually show? Okay, so this chart right here, this is the battlefield. The horizontal axis is time, with today on the left and the distant past on the right. The vertical axis shows the value of that critical acceleration A0. The predictions are crystal clear. VFT says as we go back in time, A0 should go up, following that rising blue line. The standard model says A0 should stay flat, following the red line, or maybe even go down a bit, like the green line. There is absolutely no room for confusion here. And here is the evidence. These black dots, these are the first ever measurements of A0 in ancient galaxies, all thanks to JWST. And as you can plainly see, they appear to be following the rising blue trend line exactly as VFT predicted. They are clearly not constant. This is a stunning, even if it's still preliminary, alignment with vacuum field theory. Now, this slide shows us the same data, just in a different way to double-check things. What we've done here is plot a ratio, the observed value of A0 divided by the value that VFT predicted. Now, if VFT is correct, this ratio should always be 1. And what do we see? The data points are all clustered right around that value of 1. It's another really strong piece of evidence pointing in the same direction. Now, it is absolutely crucial to remember that this is just the beginning. As the researchers themselves point out, the number of galaxies in this first study is still small, and there are some big uncertainties. It is way too early to declare victory for VFT, but this preliminary alignment is incredibly exciting, and it absolutely demands more investigation. So, let's just take a step back and think about the enormous implications here. What if this preliminary evidence actually holds up? What would that mean for how we see the universe? Well, the stakes are astronomical. If VFT is confirmed, it would be one of the biggest revolutions in the history of physics. It would mean we finally solve the mysteries of dark matter and dark energy, and that the vacuum of space itself is the key to understanding gravity. And you know what? Even if VFT is proven wrong, that's still a huge win for science. It means we can confidently rule out a major alternative and double down on our search for dark matter. Either way, we're on the cusp of a major breakthrough. Which leaves us with a final, kind of mind-blowing thought. We've spent an entire century searching for missing matter and mysterious energies. But what if the answer was right in front of our faces the whole time, hidden in the properties of nothing at all? This first glimpse from JWST suggests that the fabric of empty space might just be the most important thing in the entire universe.